Example 5 and 2.2 kind of introduces a bit more complexity to this, where we're going to solve for our angles using what the sine of theta is equal to. And I'm just going to make up an example right here that's a bit of a, just want to make sure I don't pick the first example, and I was going to. We'll just go over the technique and we'll do the first example. That's why we have them after all. So question 1, or step 1, sorry, tells us to determine which quadrants the solutions will be in by looking at the positive or negative sign. That is essentially cast. Cast tells us where things are positive. So if if let's just say as an example, if sine theta was equal to negative 0.3, I would know right away it can't be in quadrant 1 or quadrant 2 because sine is positive in those quadrants. Step 2 says solve for the reference angle. And the way that we solve for the reference angle is that we can say the relationship between sine theta and the sine of theta's reference angle is that the absolute value of the sine of the angle is always equal to the sine of the reference angle. Now, the reason why that's so important is if I was told that the sine of theta was equal to negative 0.3, I could say that the absolute value of negative 0.3 is therefore equal to the sine of the reference angle. And then using our trig from Math 10, which is worth talking about. The absolute value of negative 0.3 is 0.3. If 0.3 is equal to the sine of theta reference, what we do to solve for that angle is we take the inverse sine on both sides of that equation. And really, really importantly, if you have me for grade 10, you've probably heard me say this a million times. The reason we can do it is because we're applying an operation, the inverse sine, onto both sides of an equation, and the inverse sine and the sine cancel each other out. And so I'm left with theta reference would be equal to the inverse sine of 0.3. Now, once I know the reference angle, I could find the rotational angle in quadrant 3 and 4, which is step 3. Step 3 is to sketch our reference angle in the appropriate quadrant and then use our diagram to determine the measure of the related. And it should say angles because most of these questions are going to have 2 answers. And we'll see that right away when we get to the example itself. I am going to write this more than once. This concept is very important because it allows us to kind of bridge the gap between our angle and standard position and the reference angle that guides us to the answers. So it wants us to solve for an angle given its exact sine, cosine, or tangent value. I'm going to draw a special triangle for this so that we can talk about it. It says that the sine of theta is 0.5. Now, there's 2 special triangles that you have to know. There's the 45-degree special triangle where we have 1, 1, and root 2. And then there's the 60, 30, 90 triangle where this is 60 degrees, there's my 90, this is 1, 2, and this is root 3, and then 30 degrees is up there. Now, what we need to do is identify what would the reference angle be. And essentially what that is which angle on these 2 special triangles, when I do opposite over hypotenuse, would give me 1/2. And I'd like to do all of them. If I took the sine of 45 degrees, I would have the opposite of 1 over the hypotenuse of root 2. 1 over root 2 is not 0.5, so it's not 45 degrees. If I took the sine of 60 degrees, I would have the opposite of root 3 divided by the hypotenuse of 2. That's not 1/2, so it's not 60 degrees. But look at the sine of 30 degrees. The sine of 30 degrees, the opposite to 30 degrees is 1, and the hypotenuse is still 2. Now, what that allows me to say, and I would like to show that if I applied the inverse sine in the equation that I did right here, I could say that 30 degrees is equal to the inverse sine of 1/2. And that's basically telling me that if I have the ratio of 1 over 2 for opposite over hypotenuse, it has to be a 30-degree triangle. And that's a really, really important consequence of the special triangles, and it is often the hardest part of this section of math. Okay, I just wanted to get that out of the way because now we can work through our technique. Step 1 is we identify where sine is positive. Well, according to CAST, sine is positive in quadrant 1 and quadrant 2. Step 2 is to determine our reference angle. And I'm going to write this out, that if sine theta is equal to 0.5, then the sine of our reference angle is equal to the absolute value of 0.5. Now, that's overkill because the absolute value of a positive does nothing, but I think it is still important to think about. And then what I'm going to say then is that theta reference is the inverse sine of 0.5, which we determined was 30. So my reference angle is 30 degrees. Now, I finished saying that this solution was in quadrant 1 and quadrant 2, and I'm going to draw those solutions out. We'll do the easy one first, which is quadrant 1. There's my 30-degree angle. Maybe I'll try to draw that a little bit normally. There we go, that's a little better. So there's my reference angle. In quadrant 2, my reference angle is here. Now, I'm going to label where theta is in both of these triangles. Theta always starts at 0 degrees and rotates counterclockwise. So when we look at quadrant 1, my standard angle is equal to my reference angle. Should be a capital R. So one of my answers is 30 degrees. In quadrant 2, though, that story is a little more complex. We said that theta r was equal to 180 degrees minus theta. We know what theta r is, so you could put that in. 30 degrees is equal to 180 degrees minus some unknown. I could just move the 180 degrees over, and I get that negative 150 degrees is equal to negative theta, so theta is equal to 150. Now, in grade 11, we are only going to do this for one rotation, so from 0 to 360, and really 2 answers is as many as you're ever going to get. So we could finish this off that's saying if sine theta is equal to 0.5, then theta could be 30 degrees, or it could be 150 degrees. Now, the good news is that this is very verifiable. You could check this just by grabbing your calculator and typing in the sine of 30, I get 0.5, and the sine of 150, I get 0.5. Now, what if we did quadrant 3? In quadrant 3, 210 degrees has a reference angle of 30. That is not positive 0.5. And that's why using CAST is very important, because it identifies what quadrants our solution is in. All right, we'll do the next one here, which is a little bit of a meaner one. It's cos theta is equal to negative root 3 over 2. We're going to start with the same thing. I know that I don't need this triangle, but it is just a good routine to get into. So my 45-degree triangle is as follows, and then my 60, 30, 90 looks like this. And then what I'm going to do is I'm going to examine the cos of 45 degrees. That's equal to 1 over root 2. Now, really, really important that this is guiding us to the value, not the sign, right? So this is not root 3 over 2, positive or negative, so we're not going to include that. I can look at the cos of 60 degrees, which is 1 over 2. Or I could look at the cos of 30 degrees. Now, 30 degrees is harder because the triangle is not orientated the right way. For 30 degrees, the adjacent is root 3, and the hypotenuse is still 2. Now, I'm not getting negative root 3 over 2 here. I'm getting positive root 3 over 2, but the value is there, and that's what's important. And I'm going to write one more time that this lets me know that 30 degrees is equal to the inverse cos of root 3 over 2. That's what we're going to exploit from that information. So, using our technique now, step 1 is to identify what quadrants it's in. Because cos is negative, it cannot be in quadrants 1 or 4 because the cos of the angle is positive. My second step is I'm going to say if cos theta is equal to negative root 3 over 2, then the cos of my reference angle is equal to the absolute value of negative root 3 over 2. Now, we've gotten through chapter 7, so typically students, once they've done a couple of these questions, just kind of jump from this line to what I'm doing next, which is the cos of my reference angle should be positive root 3 over 2. Well, we identified that up above, and I kind of lost it here, that the cos of 30 degrees is root 3 over 2. So we can now say that theta r is 30 degrees. You need to get used to those special triangles enough that bare minimum, you can do what I did above here, which is to draw them out and then basically use that as a guideline as for, the sine or the cos or the tan, and then get the reference angle from that. All right, last piece of this is that we need a quadrant 2 and a quadrant 3 answer. In quadrant 2, this is my reference angle, 30 degrees. In quadrant 3, this is my reference angle of 30 degrees. But then in those answers, it is the theta that we want. So we need to determine those two rotational angles or angles in standard position. And the way that we do that, again, there's the algebraic or there's the understanding. In quadrant 2, the reference angle is equal to 180 degrees minus theta. I've actually already done this one. And what we get is that theta is equal to 150. That was the same answer from the previous question. The other piece of this in quadrant 3 is that theta reference is equal to our rotational angle minus 180 degrees. Well, if 30 degrees is equal to some theta minus 180, when I add 180 to that, I get that 210 degrees is equal to theta. So I'm just going to put that if cos theta is equal to negative root 3 over 2, then theta could be 150 degrees, and it could be 210 degrees. Now, just like before, we can check this, but there's a bit of a problem when we check it. And I want to show you that if I just type in the cos of 210, your calculator's never going to tell you negative root 3 over 2. It's going to give you the decimal version. So if you want to now confirm that you've done this correctly, you need to determine what is the negative square root of 3 divided by 2. And we see that we get the same decimal. That's a really good way of verifying these questions. This technique of verification will always work. And I'll just show you that the cos of 150 has the same number as well. Whereas, look at the cos of 30 degrees. Same reference angle, but it's in quadrant 1, or the cos of 330. Same reference angle, but it's in quadrant 4. That's how we know that it's only our quadrant 2 and our quadrant 3 angles.